Okay, so maybe we can start. So the second talk of the session is by Professor Diptiman Sen, also of the Indian Institute of Science, and he's going to tell us about effects of open ends on out-of-time order correlations and the emergence of local conservation laws in periodically driven systems in one dimension.
Okay, so let me begin by thanking the organizers, Ganpathy, Sumathi, and Yuval, for inviting me to give this talk. This is not really related to the title of this meeting, which is quantum information. Let me say that. Okay. Also, it's going to be a little bit technical. I'm going to show some calculations. If something is not clear, do stop me and ask. Okay. So this talk really has two parts. Each part done with a different student. So the first part will be work done with Samudra Sood, and the second part will be work done with Srimay Aditya. And the outline is as follows. So first, I'll very briefly tell you what is an out-of-time ordering correlator, or OTOC. And then this very well-studied model called the spin-half XY model in a transverse field, the transverse field Ising model. And then what happens to OTOCs in this model, if particularly when you have open boundary conditions. So we are looking at finite chains, not periodic systems. And you find that something interesting happens when the system is open, when you have reflections from the ends of the system. So that's the first part of the talk. The second part will be about a different model where you have just tight binding one-dimensional model with a spatially periodic potential, which is also varying periodically in time. So you'll see exactly what the model is. And there are also nearest neighbor interactions. So I'll then tell you about one of the techniques, analytical techniques we use to study that model, which is Floquet perturbation theory, and something called a Floquet Hamiltonian that you can derive from this perturbation theory. And then our results. So depending on what the parameters of this driving are, the frequency and amplitude of driving, you can get dynamical localization and local conservation laws. And when you turn on interactions and you have resonances, when all these are combined, dynamical localization, interactions, and resonances, then you get this very interesting phenomena called Hilbert space fragmentation. So we'll get to that. Okay, so what is an out-of-time order correlator? So if you have two operators, A of t and B of 0, so A of t actually is a Heisenberg operators, e to the IHT, A, e to the minus IHT. So these are two different operators. So the OTOC is defined as expectation value in the ground state, 0 temperature, or in all states for infinite temperature. The different cases one can consider of this object. So this is a product of 4 of these, and they're not in proper time ordering. That's why it's called out of time order. So B of 0, A of t, B of 0, A of t. Now, if these operators are operators with square to the identity, as they will be in our study, because we'll take them to be Pauli matrices essentially. Then the infinite temperature value, which means sum over all states of this expectation value, is related to it's 1 minus the commutator of these two operators square. Okay? And so you can see that there's this strict identity that this is less than or equal to 1. It's equal to 1 only if these two commute. So right here, you can see that you expect to see some effects like light cone, right? If two operators are outside each other's light cone, then they'll commute and this will be 1, whereas if they're inside each other's light cone, then this will be different from 1. It turns out that this OTOC is also sensitive to spreading of quantum information, unlike the two-point correlator. So we could have just looked at this, which is a simpler object to look at, but you'll see as we go along that this actually doesn't give you much information, and you get much more information from the OTOC. Okay, so what is the model that we're going to study? So we are studying the spin-half XY model in a transverse field. So this capital X, Y, Z denote the Pauli operators. So you have XX and YY couplings, and there's also a field in the Z direction. Now, it turns out this can be mapped to a model of spinless fermions by this famous Jordan-Wigner transformation. Okay, so this C is a product of Z's from one end of the system up to n minus 1, and then you have the spin lowering operator, that's Cn. and the C dagger n is the spin raising operator. So these satisfy standard fermionic anti-commutation relations. So then the phase diagram of this is well known. So it turns out that if you look at a system where Jx is not equal to Jy, first of all, and this field is less than the average of Jx and Jy, then you are in a topological phase, and there's a zero energy Majorana mode localized at each end of a system, of a very long system. If it's not long, then hybridization moves the energy away from zero. And so this is when the field is weaker than this average value. If the field H is stronger than this average value, then it's a non-topological phase, and there are no N modes. Also notice that in terms of these fermion operators that I introduced a little while ago, these X and Y operators are non-local because they have this string of operators all the way from the left end of the system up to n-1 times this operator B, whereas Z is a local operator, just a product of A and B at the same point. Okay, I should have said, so this A and B are Majorana operators, so they are equal to their own Hermitian conjugates, and they square to 1. Okay, so the important thing is that this X and Y are non-local in terms of fermions, Z is local. And we'll see that that makes a big difference to the form of the OTOC. How do we calculate these OTOCs? So there are two different OTOCs that we're going to look at. OTOCs of X, which is the non-local operator in terms of fermions, and OTOCs of Z. So these two reduce to traces of products of either 4L plus 4 or 8 Majorana operators. The 4L plus 4 is because, if there are two X operators separated by distance L, then you have a string of sigma Z's connecting them. And sigma Z is a product of two fermion operators. So that gives you this factor of 2L. And then there are 4 of these, so that gives you 4L plus 4. Whereas if it's Z, then Z is just purely quadratic in terms of fermions, and there are 4 of them, so you just get 8 operators appearing. So it's clear that the first one is computationally much harder to calculate than the second one. But in any case, they can both be calculated using Pfaffian method and Wick's theorem, and it's described in this paper. So just to contrast it with what we have done with this paper, so in this paper, they studied OTOCs in a system which has periodic boundary conditions. Actually, in a system which has, the boundaries are very far away. So they're not looking at the effects of the ends. So what we decided to study in our work is what happens when you have ends, what is the effect of that on the OTOCs? Okay, so first of all, this is the result without any driving. Okay, so we are not periodically driving anything, the static model. And you can see that there's quite a big difference between the Z OTOCs, which is on the left, and the X OTOCs. So this is the OTOC of the local operator, this is the OTOC of the non-local operator. So the top two pictures are when you're in a non-topological phase. So H is big, and the bottom two pictures are in a topological phase where H is small compared to Jx, Jy. So you notice several things here. First of all, you see this clear light cone effect. So you see these OTOCs. So this is being plotted as a function of N and T. So N is on the X-axis. This is for a 40-side system, and T is in the Y-axis. So you can see the light cone effects going back and forth between the two ends of the system. But in addition, you see that unlike the Z OTOC, which is fairly straightforward, you just see the light cone and then nothing else. The X OTOC has much more going on. So the bottom part here is when these 2 points, 0, 0, and NT are out of each other's light cone. So that part is black. So basically this is equal to 1. And that's because these two operators commute. And then after a reflection, this is all white. So this is -1. So -1 actually means that they anti-commute rather than they commute. And then after another reflection, again, it becomes dark. So you have this, successive regions of commuting and anti-commuting operators. Okay. So that's a very striking feature of having N modes. And that only shows up in this the OTOC of the non-local operator. The other thing you notice is that, so this is in the non-topological phase when there are no N modes. If you're in the topological phase, there's an N mode. So you can see the structure right at the edge. And so what is happening is that there's a mode which is localized there. And so notice that one of the coordinates of the OTOC is sitting right at the edge, this side 0. So the edge mode actually traps some of the information there. And what escapes into the bulk is therefore less than in the previous case. That's why here the color contrast is much less than here. The other thing you notice, which is not very clear here, it will become more clear later, is that there are actually oscillations as a function of time along the edge. And that we'll see has something to do with the energy difference between the two N modes, which is because of the finite size. They hybridize a little bit. Okay, so this is just a sort of warm up. This is the undriven system, time independent system. The other thing I wanted to point out is that this light cone thing, yes. Right.
Do you see any signatures of quantum chaos?
No, we don't.
Do you see this exponential divergence?
No, we don't. So actually, we went very high up in the in time, and we never found any signatures of quantum chaos. Of course, the color contrast becomes less and less as you go up, right? So when you go very far up, everything looks like the same color. But we don't really see any quantum chaos.
You don't need to solve these Schwinger-Dyson equations and all of that, or this is done?
We didn't do this. This whole thing was done purely numerically.
Well, that too has been numeric.
Yeah. So in some later work, we also put in interactions, but we never really saw clear signatures of quantum chaos. Okay. So so other thing I wanted to point out is that the slopes of these lines are related. That tells you the maximum speed of information propagation. So there are a lot of quasi-particles in the system, but the slopes are the fastest velocity that you can have of all the quasi-particles. So it's called the Lieb-Robinson bound. Okay, so there are two things. One is this, this light cone effect, and the other, as I said, is scrambling and unscrambling of information after every reflection. Let me skip all that. So just before I carry on with OTOC, I just wanted to contrast it with what happens if you just look at a two-point correlator, which is a much simpler object. But there you essentially see nothing, right? It's all the same color. You probably see very faint light cone structure, but you definitely don't see any scrambling or unscrambling. So this clearly shows that the OTOC is a much more powerful way of looking at the scrambling of quantum information than the two-point correlators. Okay, so then what we did is we took the system and we did something more, which is we periodically, we took one of the parameters and changed it periodically in time. Okay, so a few words about that. So we are going to look at periodically driven system, both in this part of the talk and the next part. So just to tell you very briefly about that, we'll have a Hamiltonian which is varying with a time period capital T. You can define a Floquet operator, which is a time ordered product of e to the minus IHT. It has to be time ordered because the Hamiltonian doesn't commute with itself at different times. Then you can, this is a unitary operator, so you can calculate all its eigenvalues and eigenstates. And then using those, you can calculate various correlation functions. Also, so this is called the Floquet operator, U. You can write this as the exponential of minus IHFT. So you can take this as a definition of HF, which is called the Floquet Hamiltonian. But because this HF is related to the log of U, you can see that you can run into problems of single valuedness. Okay, so this is well defined only if all these eigenvalues, all these phases theta n are lying close to 0, because then you can take the log uniquely without worrying about branch cuts. Okay, so there is, so basically you can calculate Floquet Hamiltonian well, very unambiguously only if the driving frequency is very large. So how are we going to drive this? So we drive the transverse field. So the transverse field in the Z direction is driven like this. So it turns out depending on the different driving parameters, so there are two parameters basically, the strength of the driving H1 and the frequency omega. There may or may not be localized N modes. So if there are N modes, the Floquet eigenvalues can be either equal to 1 or minus 1 or some other phase. Okay. Now the first two are very well appreciated. I mean, people have studied these eigenvalues for a very long time, plus 1 or minus 1 at the two ends of the Brillouin zone of quasi energies. But we have discovered that you can also get other kinds of N modes whose Floquet eigenvalues are not plus or minus 1. They are some at arbitrary point as I'll show you in a little while. So the first two eigenvalues lying at 0 and pi quasi-energy, they have a topological character. So you can calculate a winding number from the Floquet-Hamiltonian, and the winding number counts the total number of eigenvalues of these two kinds at each end of the system. The third kind of N modes, which lie at some of the phase, has no topological significance. So we'll call them anomalous N modes for lack of a better word. Now, for a periodically driven system, there's really no concept of a ground state, right? Because if you can look at the Floquet eigenvalue, calculate its eigenvalues, but because the Floquet eigenvalues only define modulo the driving frequency omega, the eigenvalues of Floquet-Hamiltonian is kind of a periodic variable. So you can choose it to lie between plus and minus omega by 2. So, so a simple thing you can do is not worry about a particular state, but calculate OTOCs as a sum over all the Floquet eigenstates. Okay, so that's called the infinite temperature ensemble. Also, we are going to calculate the OTOCs at times which are integral multiples of the time period. So stroboscopic times, basically. Otherwise, you have to worry about micromotion happening within one time period. Okay, so we are going to look at OTOCs of this form where this small t, the time is some integer times the time period. Okay, so here are some, so I'm just going to show you a bunch of pictures now. So this is one set of driving parameters. You find that there's an N mode sitting at Floquet eigenvalue +1. Okay, and so these are the corresponding, again, the Z OTOCs and the X OTOCs. The X OTOCs have this scrambling, unscrambling behavior. And once again, you can see some effect at the ends. Okay. All right, here's a different picture where you have now N modes both at Floquet eigenvalue +1 and then at two other places. They always come in complex conjugate pairs because of some symmetry in the system. And here's the third case where you have Floquet eigenvalues lying at -1. Okay, so these are just different pictures of OTOCs. So the third case, actually they're not at -1, sorry. They look like they're at -1, but these are slightly off. Here they're definitely not at -1. So these are clearly anomalous N modes. Okay, so so if you now look at the OTOCs, you discover that at the end, you see these oscillations in the OTOC. And this frequency of this oscillation is equal to the energy difference between these two. Okay, so they look almost degenerate, but they're not. They have a slight energy difference, and that's giving rise to this frequency. So this is one interesting thing, that by looking at the oscillations of the OTOC, you can actually infer what the gap between the N modes is, which may be very hard to measure in any other way. You also find that even when there are N modes at 0, the standard Majorana 0 modes, if you take a very long system, they're exactly at 0, but if the system is not that long, they'll be separated by an exponentially small amount just because of hybridization between the two ends. But because of the small exponential splitting in the energy level, you'll see oscillations. But these oscillations will be extremely long time period because the energy gap is exponentially small in the system size. So here's a picture of that. So oscillations in Z and X OTOC is very long period due to gaps between almost degenerate N modes. So at times which are 10 to the power 9 or 10 to the power 12. Okay. So that's the first part. So basically what I showed you is that for a finite system, OTOCs provide a method for detecting modes which are localized at the two ends of the system. The anomalous modes produce oscillations in the OTOCs with reasonable time periods. The other modes produce oscillations also, but at extremely long time periods. The modes at 0 quasi-energy trap the quantum information, and because of that, the OTOCs in the bulk have less of a contrast, color contrast, when you have 0 modes. These can be understood analytically in terms of wave functions of the N modes in the fermionic language. I didn't describe that, but when you look at the analytical calculation using this Pfaffian method and the Wick's theorem, you can actually get an analytical understanding of the how much information is trapped at the end and how much escapes into the bulk. For operators like sigma x, which is non-local in terms of fermions, OTOCs so scrambling and unscrambling of information after reflections from the ends of the system. Now, this is something that we are currently studying. How exactly do you understand this scrambling and unscrambling? We have some understanding now, which I don't have time to get into, but basically we have looked at the low energy excitations of the system, which are either domain walls or spin flips, depending on whether your magnetic field is large or small. And then by doing an approximation, keeping just pairs of low energy excitations, we have some understanding of why you get this scrambling and unscrambling. Okay, so I'll move on to the second part of the talk. Are there any questions about the first part, about OTOCs? Oh, this, the velocity, right?
Yeah.
Yeah. So it depends on all the parameters. It depends on the driving amplitude, the driving frequency. We don't have an analytical formula in general. We have a plot in our paper. I'll show you the reference at the end. We have a plot in the paper, but I didn't put it here. We can calculate analytically in two limits, where omega is very large. There we can, basically when omega is very large, it's you can kind of integrate over the driving, and it reduces to a time independent problem almost. And so you can calculate the velocity there. Also in the omega small limit, you can use the adiabatic approximation to calculate the velocity of this mode. So in those two limits, we have analytical formulas, but in between we don't. Yeah. Okay, so the second part of the talk. So we're going to study models on interacting spinless fermions. So they're hopping between neighboring sites. Then we have this periodic potential. So the potential can have any period. We've basically studied period 2 and period 4. So this is a potential which is varying, is alternating or maybe varying with period 4. And in addition, and the strength of this is going to be driven in time. So the spatially periodic potential is going to oscillate in time as a square pulse. It's going to be plus mu for half the time period and minus mu for the second half. And finally, we have this interaction V, density-density interaction between nearest neighbors. So it turns out that when the driving frequency and driving amplitude mu are very large compared to the interaction strength and this J, you can do a kind of perturbative calculation. So let me tell you a little bit about this perturbation theory, because this is not very well known. This is unlike standard perturbation theory where the standard kind of perturbation theory you learn in quantum mechanics for time-dependent perturbation theory. You take the H naught, the large Hamiltonian, to be time-independent, and then the perturbation is time-dependent. Here is the other way. You take the time-dependent part to be H naught, but it's a function of time, and the static part as the perturbation. So then you just grind through this formula. You find eigenstates and eigenvalues of the time-dependent part of the Hamiltonian. It's very important for this to work that the time, the eigenstates of the time-dependent part of the Hamiltonian should be themselves independent of time. The eigenvalues will keep changing with time, but the form of the eigenstate should remain the same. Otherwise, this method doesn't work. Okay, so I won't go through all the details. You find that if you start in a state, one particular state, n, just like you do in normal perturbation theory, you take one state to have amplitude close to 1 and all the other states to be close to 0, then you find that as a result of this perturbation, the amplitude of the other states is given by this formula. So many different things can happen. The numerator can vanish, and if the numerator vanishes, that means the amplitude to go to any other state vanishes. And this is called freezing. So even though you're driving the system periodically in time, the system is stuck in one particular eigenstate. The opposite can happen where the denominator vanishes, and then this is very large. Well, there clearly this perturbation theory breaks down, and then we have to do degenerate perturbation, okay, perturbation theory, or maybe go to higher orders in perturbation theory. Okay. So we have this expression for the Floquet Hamiltonian if there is when you have to do this degenerate perturbation theory. Okay, so anyway, this is a review article where we discuss all this. Okay, so so consider this time-dependent Hamiltonian that I just told you about, and the first order Floquet perturbation theory has this expression, turns out. Now this Parameter A, which appears here, is given by this pi mu by omega. So remember, mu is the driving amplitude and mu is the frequency. So you can see that you can get an interesting effect if the ratio of these two is an integer, right? Because the sign of A will be 0. And this is called dynamical localization. So essentially the hopping between nearest neighbor sites as a result of the driving has become 0. Okay, and then you're just left with the interaction part. So this is quite a peculiar system, right? There's essentially no kinetic energy and it's totally dominated by the interaction part. And then you get a number of many body flat bands with discrete values of the energy. Okay, so if you now look at, so first of all, let's look at the quasi-energy spectrum. So remember, these are the eigenvalues of this Floquet Hamiltonian. So they form these discrete sets. Okay, so basically these are just the eigenvalues of this operator, which is a very simple operator to think about. Okay. So this is when you are at a dynamical localization point. Omega is 20, mu is also 20. So the ratio of the two is 1. Okay. 5 minutes, I guess. Okay. Whereas, this is the entanglement spectrum. So here again, you see that there are some particular lines which are these sort of discrete set of states with definite values of the quasi-energy. That's the maximum possible value you can have. It's called the page bound. Sorry. This is what happens when you go slightly away from dynamic localization. So here omega is 20 and mu is 20, omega is 22. So you lose this dynamic localization. Now your quasi-energies are all over the place. They're not discrete values anymore. And this entanglement entropy plot versus the quasi-energy also broadens out. I think I'll skip all this because I won't have the time. Let me skip all this because I'm really running out of time. So, okay, so the stuff that I skipped is about the period 4 model. So I can tell you about that later if anyone asks me after the talk. So in the period 2 model, the next thing we studied at is what happens. So remember the Floquet perturbation theory was when mu and omega were very large compared to the interaction V. But we also looked at what happens when they're all equal. Okay, so it turns out you can still do a first order Floquet Hamiltonian here. And now you get something very interesting. So first of all, because mu is equal to omega, you get dynamical localization. And secondly, when that's also equal to V, you get something like a resonance. In other words, going from a state where two particles are not next to each other to a state where they're next to each other, that state, the energy difference is V, but that's the same as the driving frequency omega. So there's a perfect resonance in going from one state to the other. And then the first order Floquet Hamiltonian has this form. So this is a kind of correlated hopping. So you can hop between two sides, J plus 1 and J plus 2, provided the occupations at J and J plus 3, they're neighbors on the two sides, if they're different from each other. So either this one is 1, the other one is 0, then you can hop in between, or this one is 0, the other one is 1, then you can hop in between. Okay, so you can show that this is a very interesting Hamiltonian. Because of this kind of correlated hopping, the Hilbert space breaks up into fragments of different sizes. Okay, so you have 2 to the power L states, but they break up into a huge number of fragments. By fragments, I mean states in different fragments don't connect to each other through this Hamiltonian. Okay. So if you started your system off in one of these fragments, it stays in that fragment forever. This is, of course, just the first order Floquet Hamiltonian. This is going to go away as you increase, if you go to higher orders. But just to continue with this, let me give you an example of a fragment. So as a result of this, if you look at this state where these are all occupied and these are all empty, because of this Hamiltonian, you can only move between these 4 states where you just move one side and then you come back. So this is a fragment with 4 states. There are also many fragments which have only one state, which are basically frozen. You can't go from those states to any other states. And you can show the number of these fragments grows exponentially, even though it's a smaller exponential than the total number of states, which is 2 to the L. Okay, so we are now studying Hilbert space fragmentation in more detail, but I just wanted to show you that it can arise in this system with periodic driving. So the summary is that periodic driving of systems with periodic potentials, so it's periodic in both space and time, can give rise to local conservation laws at special values of the driving parameter. This part I actually skipped, that you can also get the SSH model by driving the period 4 model, which is skipped. And then a combination of dynamical localization, interactions, and resonances gives rise to Hilbert space fragmentation. This also I skipped. So there are these pictures of Loschmidt echo, which I skipped over. You find that Loschmidt echo doesn't decay for a very long time. Eventually it decays, because eventually the higher order terms appear and system will actually thermalize. But it doesn't thermalize for a very, very long time if you're sitting exactly at one of these dynamic localization and resonant points. So one of the problems that we want to study at some point is how do this lack of thermalization, how does it disappear at higher orders? And so there's a very long pre-thermal state and then eventually it thermalizes. So we need to understand that better. Okay, so I'll stop here. So these are the references. The first, the OTOC part is in this paper, and the local conservation laws and Hilbert space fragmentations in this paper. So thank you.
Thank you very much. Questions?
I have a question about first part.
Okay.
So you saw no evidence of quantum
Yes.
chaos. No, it's an integrable system because it's an X-pi model in a Z field.
Right.
And there's no drive, so it is integrable. So you don't expect.
Yeah.
to get-
Actually, it's integrable even with driving, because it is a quadratic
Right.
model.
But if
Yeah.
you have a weak, say, next nearest neighbor interaction,
Right.
which you can still write it as a local object formula,
Right.
that is an irrelevant operator, but it will actually break the integrability.
Yes.
So that will give you quantum chaos, will be rather weak quantum chaos. It will give you quantum.
Yeah. So we have studied that. We didn't go very far, so it's not shown here. But we did study what happens if you add a weak interaction, ZZ interaction, for example.
That is still integrable.
Yeah. So we
You get the answer.
it's
the answers in
still
that
integral with
But
beta
you
and
just
Z.
put an X-pi model with and put the next nearest neighbor interaction.
Right.
Then it's
Or we,
quartic.
yeah.
It's a quartic term in fermions.
Okay.
And it's,
So you can have, yeah. So for example, if you have an XYZ model and a field,
Yeah.
then it's not integrable. Yeah. So we studied that. So we didn't go to very large times. One thing we found is that the scrambling, unscrambling effect definitely goes away.
that was my other question. How do you actually
Yeah.
investigate the scrambling? How do you know that it's scrambling?
We're just calling this scrambling. The fact that the OTOC in this region is very different from here. So here the OTOC is close to 1, here is different from 1. And so that's basically saying that your operators X of t here and X of 0 don't commute with each other.
Because
So
usually one interprets, one estimates scrambling in terms of this, in terms of quantum chaos. And the existence of a Lyapunov exponent.
yeah, but this is, as Eduardo said, this is actually integrable. So there's no Lyapunov exponent here. Yeah.
Clearly some dynamic.
Yeah. And somehow, yeah, it's getting unscrambled after the first reflection. Yeah.
Yeah. So in the periodically driven model, when you vary mu as a function of t, and with the finite size system, you have the Z2 breaking.
This
right?
first part, this OTOC part.
In the first
yeah.
part.
Yeah.
So which in the fermion language would mean fermionic parity sectors, as we had studied long ago. So do you
Right.
see any of the, because the coupling of the two modes at the two edges of the system, you have two sectors. So do you see any of the signatures of that?
No, we just calculate OTOC as a sum over all states. So it includes both fermion parities.
Okay, both.
Yeah. We didn't look separately at the contributions from the different parity sectors.
I see.
Right.
Yeah, no, just continue with this discussion. So if you consider the TJC model,
Right.
okay, the TJC model is quasi exactly so.
So
in the
TJ,
TJC, not the TJ model, the TJC.
what's
So
the
there is,
C? Yeah.
it is instead of being SI, Z. instead of in SI Heisenberg,
Oh,
is
okay,
SC.
Oh, I see. Okay,
So
fine.
that model was exactly solvable. So indeed, Motrunich, indeed was talking about precisely Hilbert space fragmentation in that model, because that model, the low energy sector, basically maps onto an how do you say, the model that you have in the second part,
Right.
that is an XXZ model.
Right.
Okay, so in that case, you are going to have different subspaces. So my question is, going back to his question about chaos, what happens if you drive that system where you have different subspaces, you still have fragmentation, but the model is not integral. The full model is not integral.
Right.
So
Okay.
there you may see some chaos.
Okay, all right. Okay, so I really don't, yeah, you'd have to look at that model and see what happens. Yeah, yeah, yeah. No, I understand that. We haven't studied anything like that.
Other questions? Maybe something from the students? Yes.
Yeah, so what was the motivation of considering OTOC at infinite temperature?
Oh, because, so we were really looking at the periodically driven system. Now, if you have a system which is periodically driven, there's no particular special state. I mean, there's no concept of a ground state, right? Because the energy is not conserved when you drive something periodically. So there is no ground state to consider. So the most democratic thing to do is to sum over all possible states. And that's what we did. After this, we have done Samudra and I have done some more work now where we are just looking at this model without driving, and then we look at the ground state OTOC. Just one state, the zero temperature OTOC. But we get very similar features even there. This scrambling, unscrambling, this light cone effect. So all these effects don't really depend on which states you look at. Okay. So it's just that because it's periodically driven, we just summed over all possible states. That was the simplest thing to do. But you get a very similar thing if you just look at the ground state OTOC.
Okay.
One last question from there, and maybe we can take it off.
Hello. So I want to ask about this OTOC, like how it can be good measure for quantum chaos. And also if we consider in your model this quasi-periodicity, then it might lead to this chaotic behavior.
Right. So as Eduardo was asking, we don't actually see any effects of quantum chaos. I mean, we did look at models which are not integrable. Maybe we didn't go to large enough times, but at low times where we just looked at a few oscillations, we don't see any effects of chaos. Okay, so you just see this kind of pattern continuing. Now, yeah, so we don't really understand how to use OTOC to study quantum chaos.
Have you considered these spectral form factors also?
No, we have not done that.
Other question from this fragmentation, Hilbert fragmentation. So, Hilbert space fragmentation. So here, like, can we introduce some kind of mechanism which can break this fragmentation so that different part of the Hamiltonian can talk to each other again, like breaking this local symmetry or
Oh yeah,
responsible for
yeah. So unfortunately, I skipped over all those slides. So the Hilbert space fragmentation was only something we see at first order perturbation theory. But then we have pictures of what actually happens when you do, you numerically evolve the system, this periodically driven system. And then you can see that eventually it thermalizes. Okay. Let me see if I can show you. So here's one of the pictures, for example, with the Lock-Schmidt echo. Right. So you can see that, so this is, we are at a dynamical localization point. So this is not a Hilbert space fragmentation, sorry. But the pictures are very similar. If you are sitting exactly at some point where you have dynamical localization and resonance, then you'll see this. So Lock-Schmidt echo is basically this object. It is the matrix element between some initial state chosen in some way. Then you evolve it for n time periods and then the overlap with the initial state, mod of that. You can see that if you sit at carefully chosen driving parameters, this oscillates for a very long time, but eventually it will decay. So this is when you're exactly sitting at a dynamical localization point, and this is when you're slightly away. Here omega is equal to mu, here omega is slightly different from mu. And so this is a generic thing that happens. Eventually the thing will thermalize. It's just that if you're sitting at one of the special points, it doesn't thermalize for a long time. But we don't really understand. We would like to actually calculate what this decay time rate is. Right. We have not done that.
All right. Let's thank Diptiman again.
Yeah, thanks.